Nobody knows how a magnet works. That is not a joke. Pick up the thing holding a photograph to your refrigerator door, and you are holding something no physicist alive can explain to the bottom. They can describe it perfectly. They can predict the magnetic strength of a single electron inside it to 12 decimal places, the most accurate prediction in the history of science. They can show you that magnetism is really electricity, seen from a moving frame, produced by particles drifting slower than a snail. They can hand you a theorem from 1911, proving that in the physics most people believe in, that magnet cannot exist at all. And when you ask the last question, why, every one of them stops in the same place. By the end of tonight, you will know exactly where that place is and why nobody has ever got past it. Before we begin, if slow walks to the edge of what physics can say are how you like to fall asleep, a like or subscribe really helps the channel grow. It means a great deal to me. Now, let's begin. There is an object in your kitchen that nobody on Earth can fully explain. It is probably holding a photograph, or a receipt, or a note about an appointment you have been meaning to reschedule. It weighs a few grams. It cost almost nothing. You have touched it 1,000 times without thinking about it once. And if a child were to walk up to that refrigerator door tonight, pull the magnet off, put it back on, and ask you how it works, you would find yourself in the strangest conversational position in all of physics. Because the honest answer is not that you do not know. The honest answer is that nobody does, and the reason nobody does is far more interesting than ignorance. Let me show you what I mean, because this is not a trick, and it is not a word game. Every step of the explanation I am about to give you is real, tested, and correct. The problem is, what happens when you keep asking? Start where a school textbook starts. Certain metals, most famously iron, feel a force when they are brought near a magnetized object. Sometimes that force pulls, sometimes it pushes. That is the first layer, and it is a description rather than an explanation, so you ask again. Why is there a force? Because the magnet produces a field around it, an invisible arrangement of influence filling the space, and any piece of iron placed inside that arrangement responds to it. That is layer 2, and it is genuinely better because now you have a mechanism with a shape. So you ask again, where does the field come from? From moving electric charge. Whenever charge moves, a magnetic field appears around it. Inside a solid piece of iron, the moving charges are electrons, circulating around their atoms and also carrying something called spin. You could stop there. Most explanations do. But the child is not finished, and neither is the physics, so you go down another step. Why does iron have a field when a copper coin does not? Because in most materials, those tiny electron magnets point in every possible direction and cancel each other out to nothing. In a very small number of materials, they line up instead. Enormous numbers of them, all pointing the same way at once. And the sum of all those tiny alignments is a force you can feel with your hand. That is layer 4, and it is the last layer that most people ever hear. Now it gets strange. Why do they line up? And here the answer changes character entirely, because the electrons in iron do not line up for magnetic reasons. They line up because of a quantum rule about identity, a rule saying that 2 electrons of the same spin are forbidden from occupying the same state, which forces them to keep their distance, which lowers the electrical energy of the whole arrangement. The alignment that makes a magnet is a side effect of electrons refusing to share. The force holding that photograph to your door is, underneath, electricity wearing a disguise it borrowed from quantum statistics. You have now gone 5 levels down, and you are still nowhere near the bottom. Ask what the field itself is made of, and you arrive at quantum electrodynamics, the theory that treats the electromagnetic field as a quantum object and describes the force between charges as an exchange of particles of light, too fleeting to observe directly. Ask what electric charge is, and you get an answer, involving a symmetry of that field. Ask what spin is, and the answer is that spin is an intrinsic property of the electron, a kind of angular momentum that exists without anything rotating, and that is where it stops. Not because someone has not gotten around to it, not because the next paper will fix it. It stops because charge exists, and spin exists, and the electromagnetic field exists, and when you ask why, there is no further layer left to point at. The universe simply has these things. Physics has pushed the question down about as far as it can currently be pushed, and at the bottom of the last step, there is a statement with nothing underneath it. Charge is. Spin is. The field is. Because it is. I want to be careful here, because there is a lazy version of this idea, and it is not the one I am describing. The lazy version says that science does not really understand anything, and therefore all explanations are equally good. That is nonsense, and the rest of tonight will show you exactly why. What I am describing is something more precise and much stranger. Magnetism is one of the most thoroughly understood phenomena in the history of human thought. We can predict the magnetic strength of a single electron to 12 decimal places and get it right. We can build a machine that photographs the inside of a living brain by leaning on that strength. And still, at the very bottom, there is a shrug. The shrug is not a hole in the science. It is the shape of what explanation is. The physicist Richard Feynman was asked about exactly this, on camera, in an interview filmed in 1983. The interviewer wanted something simple. Two magnets push each other apart. What is going on in the gap between them? What is doing the pushing? Feynman would not answer, not because he could not, but because he could see the trap in the question, and instead of walking into it, he did something better. He built an analogy, and I want to walk you through it slowly, because it is the key to everything that follows. Suppose, he said, you ask why a woman is in hospital. Somebody tells you she slipped on the ice and broke her hip. That is an answer, and for most purposes it is a complete one. But you can ask again, why did she slip on the ice? Well, because ice is slippery. Fine. Why is ice slippery? That one is genuinely difficult, and the usual answer involves the peculiar behavior of water, which expands when it freezes, so that pressure from a foot can melt a very thin layer and leave you standing on liquid. Good. Why does water expand when it freezes, when almost nothing else does? Because of the geometry of the bonds between water molecules, which hold them in an open lattice with more empty space in the solid than in the liquid. Why do those bonds have that geometry? Because of the shape of the electron orbitals in oxygen and hydrogen. Why do electrons arrange themselves that way? You see what is happening. There is no last step. And there is also a second chain running in parallel, because you could just as easily have asked why she was outdoors at all, and why her balance was not what it was at 30, and whether she was distracted, and what she was hurrying toward. Feynman's point was that a why question only has an answer relative to a set of things the person asking is already willing to accept without further question. Explanation is not a ladder to bedrock. It is a translation of the unfamiliar into the familiar, and it stops when it runs out of familiar. Magnetism is unusual because it sits so close to the foundations that there is almost nothing familiar left underneath it to translate into. That is why a perfectly reasonable question about a perfectly ordinary object leads, in about 6 sentences, to the edge of what physics is able to say. There is a cultural footnote to this that I think about more than I probably should. In 2010, a song was released whose lyrics asked, in plain and slightly exasperated language, how magnets work. The line became an internet punchline for years. It was held up as a monument to scientific illiteracy, quoted by people who wanted to signal that they, at least, understood how the world was put together. And the uncomfortable fact is that almost none of them could have answered the question either, and the ones who could would have arrived, within a minute or two, at exactly the same shrug we just found. The question was not stupid. The question was the last question, and it was written on a refrigerator door. So here is what I am promising you for the next 2 hours. We are going to walk down that chain properly, one step at a time, and we are going to take every step seriously. You will see the moment two separate forces turned out to be one force, discovered by accident in front of a lecture hall. You will see why the most famous picture of magnetism in every classroom on Earth is actually a photograph of interference. You will see magnetism dissolve into electricity the instant you start moving, and you will see a particle that has angular momentum without rotating. You will find out why a theorem from 1911 proves that the magnet on your fridge should be impossible. You will go down into the core of this planet, which is 4 times too hot to hold any magnetism at all, and is magnetic anyway. You will look through the eye of a small brown bird that appears to see the field as a shape in the air. And at the end, I am going to answer the question in the title, as plainly as I can. Not dodge it, not soften it, but tell you exactly why the most mysterious force in physics is still, after 400 years of the best work anyone has ever done, something we cannot explain. But not yet. First, we have to go back about 2,500 years, to a rock. Somewhere in the ancient world, a person picked up a stone and noticed that it stuck to a piece of iron. We do not know who, and we do not know when. What we know is that the stone was magnetite, an iron oxide that occurs naturally in the ground, and that certain pieces of it come out of the earth, already magnetized. The Greeks called it after Magnesia, a district in Asia Minor where it was found. In English, it acquired a better name, Lodestone, the leading stone, the stone that shows the way. There is a detail about Lodestone that I find quietly satisfying. Ordinary magnetite is not strongly magnetic. The steady field of this planet is far too weak to magnetize a rock sitting in the ground. So for a long time, it was unclear why any natural stone should be a working magnet at all. The best available answer is lightning. A lightning strike drives an enormous current through the ground for a fraction of a second, and the field pulse around that current is thousands of times stronger than anything the planet produces on its own. The stones that humans found lying on the surface, the ones that would pick up an iron nail, appear to have been magnetized by strikes. Every lodestone in every ancient collection was a fossil of a storm. The first people to make systematic use of the stone were in China, and they did not use it for navigation. They used it for divination. The device was called the Sinan, and descriptions of it go back to around the 2nd century before the Common Era. It was a spoon carved from lodestone, balanced on a polished bronze plate, marked with directions and constellations. You set the spoon spinning, and when it settled, the handle pointed south. The plate was a diviner's board. The question being asked was not, "Where am I?" The question being asked was, "Where should this house face? What will this year bring? What does the arrangement of the world say about the arrangement of a life?" I want you to sit with that for a moment, because it is a genuinely reasonable response to the situation. Somebody hands you a rock that always points the same way for no discernible cause. There is no wind pushing it. Nothing is touching it. It is not heavier on one end. It simply knows a direction, and it knows it in a locked room, in the dark, underground, on a boat. If you have no concept of a field, no concept of charge, and no concept of a planetary interior, what exactly is the sober hypothesis? The stone is in communication with something larger than the room. That is not superstition. That is, in the most literal sense, correct. The turn toward navigation took a very long time. The first unambiguous written description of a magnetized needle used as a compass comes from Shen Kuo, a Chinese polymath whose dream pool essays were written around 1088. Shen Kuo describes several ways to mount the needle: floating it on water, balancing it on a fingernail, hanging it from a single silk thread with a piece of wax, and he notes, in passing, that the silk thread version is the most reliable. Then he records something that nobody in the world had written down before. The needle, he says, does not point exactly south, it points a little to the east of it. That is the first known observation of magnetic declination, the fact that magnetic north and geographic north are not the same direction. It would take another 800 years before anyone had the faintest idea why, and we will get to the reason later tonight, and the reason is stranger than the observation. But there it is, in an 11th century notebook, written down accurately by a man who could not possibly have explained it, and who wrote it down anyway because it was true. By 1117, a text called the Pingzhou Table Talks describes ship's navigators using the compass in poor visibility, watching the needle when the stars were hidden. The instrument had crossed from the diviner's table to the deck. Within a century or so it appears in Europe, first mentioned around 1190 by the English scholar Alexander Neckham, and the European reception was, at first, mixed in a way that is worth mentioning. There are accounts of sailors being reluctant to use the device, and of its behavior being regarded with suspicion rather than gratitude. A needle that moves without being touched sits uncomfortably close to a category of explanation that the period took very seriously and very badly. Then, in 1269, something remarkable happened. A soldier and scholar named Peter Peregrinus, camped outside a besieged town in southern Italy, wrote a letter about magnets to a friend back home. The letter, known as the Epistola de Magnete, is the first genuinely experimental study of magnetism anywhere in the world. Peregrinus did not speculate about the influence of the heavens. He took a lodestone, ground it into a sphere, and moved a small iron needle across its surface, marking the direction it took at each point. The lines he drew converged on two opposite spots. He called them poles, borrowing the word from the sky, and the word has never left. Then he did the experiment that matters most. He broke a magnet in half, expecting, as anyone would, to be left holding a north in one hand and a south in the other. Instead, he had two complete magnets, each with its own north and its own south. He broke those. 4 magnets. There was no way to isolate a single pole. He recorded the result plainly and moved on, and it would be nearly 700 years before anyone understood that he had bumped into one of the most stubbornly unexplained facts in all of physics, which we will come to shortly. The last figure in this stretch of the story is William Gilbert, physician to Queen Elizabeth I, who published a book called De Magnete in 1600. Gilbert did what Peregrinus had done, and then took it somewhere new. He made a magnetized sphere of lodestone, which he called a terrella, a little earth, and he moved a small compass needle around its surface. And he found that the needle did not merely swing horizontally, it also tipped. Near the sphere's equator, it lay flat. Near the poles, it stood almost on end, pointing into the stone. Sailors had already noticed the same thing on the open ocean. Compass needles in northern waters had a tendency to dip, and instrument makers compensated by weighting the other end. Gilbert put the two observations side by side, and drew the conclusion that gives his book its most quoted line. The earth itself is a great magnet, not a mountain of lodestone at the pole, as some had supposed, not an attraction from the stars. The entire planet, the whole ball of it, behaving like the small stone sphere on his table. That is an extraordinary piece of reasoning, and it was right, and it was arrived at with a rock, a needle, and a willingness to look. Gilbert also gave us the word electric, from the Greek for amber, for the entirely separate force that made rubbed amber pick up straw. He was quite certain the two phenomena were unrelated. Everybody was, for another 220 years. So look at where 2,000 years of work had gotten us by the year 1600. Humans could locate the poles of a magnet, could map its field with a needle, could show that a magnet cannot be cut into halves, could measure the dip and the declination, could navigate an ocean with it, and could correctly conclude that the planet they were standing on was a magnet the size of a world. Every one of those achievements is accurate. Not one of them is an explanation. If you had asked William Gilbert what magnetism actually was, he would have told you it was a soul-like property of the earth, an animate virtue in the stone, and he would have said it with the confidence of a man who had just done the best experimental work of his century. They could use it perfectly. They could not explain it at all, and I want you to hold that arrangement in mind, because when we reach the end of tonight, we are going to find ourselves standing in a version of the same place, with better instruments, better mathematics, and a description accurate to a part in a trillion, still unable to say what the thing is. The wall they were about to hit was not going to be broken by a better lodestone. It was going to be broken by a completely unrelated accident in a lecture room in Copenhagen in the spring of 1820. Hans Christian Oersted was giving a lecture demonstration in Copenhagen in April of 1820, when a compass needle on his bench moved for no reason anyone in the room could name. He had been showing his students what happened when current from a battery ran through a thin platinum wire. The wire heated, that was the demonstration, but there was a compass sitting nearby, left over from something else, and when the circuit closed, the needle swung, not toward the wire, not away from it, sideways, at right angles, as though it were trying to wrap around the wire rather than approach it. Nobody knows for certain whether Oersted had been half expecting this. He had been interested for years in the idea that the forces of nature were secretly unified, an idea he had picked up from German philosophy rather than from any experiment, and he had apparently tried something similar before without success. What is certain is that he did not immediately publish. He spent 3 months repeating the experiment with better batteries, thicker wires, the compass above the wire and below it, and only in July of 1820 did he send out a 4-page pamphlet in Latin describing the effect. Understand what that pamphlet did. For 2,000 years, electricity and magnetism had been two separate curiosities. Rubbed amber picked up straw. Lodestone picked up iron. There was no reason to think they had anything to do with each other, and Gilbert, who knew both phenomena better than anyone alive, had explicitly said they did not. Oersted's 4 pages ended that. An electric current makes a magnetic field. The two curiosities were one thing. The response across Europe was close to a stampede. André-Marie Ampère heard the news in Paris in September of 1820 and, within a matter of weeks, had done the obvious next experiment and several non-obvious ones. If a current makes a field, and a field pushes a magnet, then a current should push another current. It does. Two parallel wires carrying current in the same direction attract each other. Carrying current in opposite directions, they repel. Ampère worked out the force law, and then went further and proposed something that sounds almost modern, that all magnetism, including the magnetism of a lodestone, is caused by tiny circulating currents inside matter. He had no way to see them, and no idea what would be doing the circulating. He was, in outline, right. Then comes Michael Faraday, who is one of my favorite people in the history of science, partly because of what he did, and partly because of how he did it. Faraday had almost no formal mathematics. He had been a bookbinder's apprentice. He had educated himself out of the books he was binding, and he thought in pictures rather than equations for his entire life. In 1821, he built a device in which a wire carrying current rotated continuously around a fixed magnet, suspended in a bath of mercury. It did no useful work, and it powered nothing. It is the ancestor of every electric motor on this planet. 10 years later, on the 29th of August, 1831, Faraday wound 2 separate coils of wire onto opposite sides of an iron ring. One coil was connected to a battery. The other was connected to a galvanometer and to nothing else. The 2 circuits never touched. When he closed the switch on the first coil, the needle on the second circuit kicked. Then it fell back to zero, even though the current in the first coil was still flowing. When he opened the switch, the needle kicked again, the other way. That kick is the whole of modern civilization. A steady magnetic field does nothing. A changing magnetic field creates an electric field, which drives a current in a wire that is not connected to anything. Every power station on Earth is a machine for changing a magnetic field near a coil of copper. The electricity in the wall behind you tonight came from a spinning magnet. Faraday found one more thing that mattered enormously, and almost nobody outside physics has heard of it. In 1845, he sent a beam of polarized light through a block of heavy glass with a strong magnet arranged around it, and the plane of polarization rotated. Turn the magnet off, and the rotation stopped. This is now called the Faraday effect, and at the time, it was the first direct evidence that light and magnetism were connected at all, that whatever light was, a magnetic field could reach into it and twist it. Faraday had no theory for why. He had spent years looking for exactly this connection, on the conviction that the forces of nature had to be one thing, and when he finally found it, he could describe it perfectly and explain it not at all. That sentence is going to keep coming back tonight. There is also a quieter figure in this story who deserves a line. Carl Friedrich Gauss, working in Göttingen, made the first absolute measurement of the strength of Earth's magnetic field in 1832 and founded an observatory that began recording the planet's field continuously. Until Gauss, magnetic strength could only be compared. This magnet is stronger than that one. After Gauss, it could be stated as a number, in units of mass and length and time, with no reference magnet required. That sounds like bookkeeping. It is the difference between a curiosity and a science, and it is why we can say today, with confidence, exactly how much the field has weakened since the 1830s. We will need that number later. Faraday also gave us the mental image that the entire subject now runs on. He could not do the mathematics, so he drew. He pictured space around a magnet as filled with lines of force, curving out from one pole and back into the other, under tension along their length and pushing apart sideways, like a bundle of stretched elastic. The lines were his way of thinking without algebra. Established physicists of the period regarded them as a crutch for a man who had not learned the proper tools. Then James Clerk Maxwell read Faraday and did something nobody expected. Rather than dismissing the lines of force, he took them completely seriously and asked what mathematics would have to be true for that picture to hold. Between 1861 and 1865, he assembled the results of Oersted, Ampere, Faraday, and Gauss into a single system of equations, and in doing so, he found that the existing laws were not quite consistent with each other. There was a gap, and to close it, he had to add a term that nobody had measured, a term saying that a changing electric field produces a magnetic field, just as a changing magnetic field produces an electric one. He called it the displacement current. Adding that term did something Maxwell had not gone looking for. With it, the equations permit a solution in which a changing electric field creates a magnetic field, which changes, which creates an electric field, which changes, and the whole arrangement propagates through empty space without any matter to carry it. A self-sustaining disturbance of the field, a wave. And the equations told him how fast it would travel. The speed was determined entirely by two constants that had been measured in the laboratory years earlier, in an experiment that had nothing to do with light. Weber and Kohlrausch had measured them in 1856 by comparing electrical units. Maxwell put the numbers in. The answer came out at about 310,000 kilometers per second. The measured speed of light at the time was about 315,000 kilometers per second. Maxwell wrote that the agreement seemed to show that light and magnetism are affections of the same substance. and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. He had not set out to explain light. He had set out to tidy up some equations about wires and compasses, and light fell out of the mathematics, unrequested, at the correct speed. I want to be honest about how large that is. Everything you see, at every moment of your life, is a ripple in the same field that makes the note stick to your refrigerator. The warmth of sunlight on your face, the signal reaching the device you are listening on, X-rays, radio, the color of the sky, all of it is one phenomenon, and Oersted found the first thread of it because a compass twitched next to a hot wire. So by about 1865, physics has an achievement of genuinely historic proportions. 4 equations, later polished into their modern form by Oliver Heaviside in 1884, describe every classical electromagnetic phenomenon there is: motors, generators, radio, the behavior of every magnet ever made. You can compute what will happen in essentially any arrangement of charges and currents, to whatever accuracy your instruments can check. And now watch what happens when the child at the refrigerator door asks the question again. What is the field made of? Maxwell's equations do not say. They tell you how it behaves, everywhere, always, with total reliability. They tell you nothing about what it is. Maxwell himself spent years building elaborate mechanical models of the field, spinning cells, idle wheels, an invisible medium under stress, trying to make it into something you could picture. None of the models survived. The equations did. Why does moving charge make a magnetic field? The equations do not say. They say that it does. And here is the part that should make you uneasy in the right way. The 19th century took this framework as the near final word on the subject, and it contained, hidden in plain sight, 2 things that would break it open. One of them was an asymmetry so obvious that it is visible in the shape of the equations themselves, an open confession that something is missing. The other was a contradiction about who is moving, sitting quietly, in the difference between Faraday's ring experiment and Oersted's compass. We are going to take the confession first, and to find it, we have to go back to a piece of paper covered in iron filings. The picture you have seen 100 times and have almost certainly misunderstood. You have seen this image. Almost everyone has. A sheet of white paper lies flat on a table. Underneath it, a bar magnet. Someone takes a pinch of iron filings between finger and thumb and lets them fall. And at first, they land as a grey scatter, meaningless. Then a finger taps the edge of the paper. The filings jump, settle, jump again, and something takes hold of them. They stand up on end. They gather into curves. 2 dense knots form over the ends of the magnet, and from each knot, the filings arrange themselves into arcs that sweep out, bow away from the paper's center, and come back down into the other knot. Tap again, and the pattern sharpens. There is no wind. Nothing is touching them. Every filing has found its place in a shape that was already there before any of them arrived. That is the moment most people first believe in fields. It is genuinely one of the great demonstrations, and I do not want to take it away from you, but I do want to tell you what you are actually looking at, because it is not what you think. You are not seeing the field. Each of those filings, the moment it enters the region around the magnet, becomes magnetized itself. It becomes a tiny bar magnet with its own north and its own south, and it produces its own field, which adds to the field around it. Then it lines up with the total, which has now been changed by its own presence, and by the presence of the filing next to it, and by the presence of every other filing on the page. The arcs you see are not the field. They are the field plus the response of the measuring instrument, and the measuring instrument is thousands of individual objects all interfering with each other and with the thing they are supposed to be revealing. Now picture the same sheet of paper before anything was sprinkled on it. The field is there. It is exactly as real as it was a moment ago. It fills that space. and a great deal of space beyond the edges of the paper, and it is completely, permanently invisible. There is no way to see it that does not involve putting something into it, and there is nothing you can put into it that does not change it. I find this genuinely lovely rather than frustrating, but it is worth being precise about the size of the problem. The most reproduced image of magnetism in every classroom on Earth is a picture of the observer's interference, and the lines themselves are not real either. Faraday drew them because he thought in pictures, and physics kept them because they are useful, but there is no true number of lines. You draw them denser where the field is stronger, and further apart where it is weaker, and between any two lines you have drawn, there are infinitely many more you could have drawn instead. The field is smooth and continuous everywhere. The lines are a human accounting habit laid over the top of it. Which brings us to the confession. When Maxwell's equations are written out in their modern form, there are 4 of them, and 2 describe how field lines begin and end. The first one, for electricity, says that electric field lines start on positive charges and finish on negative ones. That matches everything you know. Charge comes in isolated lumps. There is such a thing as a single electron, alone in space, with a field radiating outward from it and going nowhere in particular. The second one, for magnetism, says something different and much stranger. It says that magnetic field lines never begin and never end. Not anywhere, not ever. Every magnetic field line in the universe closes on itself in a loop. Written in the compact language of the subject, it is about the shortest statement in all of physics. The divergence of the magnetic field is 0. In plain terms, it means there is no such thing as an isolated magnetic pole. Peter Peregrinus found this in 1269 with a hammer. Break a magnet in half, and you do not get a north and a south. You get 2 magnets. Break them again, and you get 4. There is no depth at which this stops. Grind the magnet to powder, and every grain is a complete magnet. Go all the way down to a single iron atom, and it is still a dipole, still with 2 ends, still impossible to separate. Nobody in the 800 years since has ever produced, found, or observed a magnetic monopole, a north without a south, an object from which field lines genuinely radiate the way they radiate from an electron. And there is no accepted reason for this. That is the part that ought to bother you. Everything else in Maxwell's equations is beautifully symmetric between electricity and magnetism. And then, in one specific place, the symmetry simply stops, with no explanation attached. The equations are not saying monopoles are impossible for some underlying structural reason. They are saying we have never seen one, so we set that term to 0, and it has stayed at 0 for 160 years. In 1931, Paul Dirac made this much worse, in the best possible way. He asked what would happen if a single magnetic monopole existed anywhere in the universe, just one, at any distance, at any time in history. Working through the quantum mechanics of a charged particle moving in the field of such an object, he found that consistency demanded something remarkable. Electric charge would have to be quantized. It would have to come in exact whole number multiples of one fundamental unit, with no intermediate values allowed. Now, charge quantization is an observed fact. It is one of the most precisely verified regularities in nature. Every electron in your body carries exactly the same charge as every other electron, to a precision beyond anything that could be coincidence, and every proton carries exactly the opposite. Nothing in the standard picture explains why. Dirac's argument says that if one monopole exists, somewhere, then that fact is explained. One object, anywhere in the universe, and one of the most fundamental regularities in physics, falls into place. So the absence of monopoles is not merely a gap, it is a gap where a beautiful explanation would fit perfectly if only something would show up. On the 14th of February, 1982, something did. Blas Cabrera had a superconducting detector running at Stanford, a loop of superconducting wire designed so that if a monopole passed through it, the current in the loop would jump by an exact, calculable amount and stay there. It had been running for months, recording nothing. Cabrera came in after the Valentine's Day holiday, looked at the chart, and found a single clean step in the record. One jump, of very nearly the exact size Dirac's theory predicted for a single monopole. It has been called the Valentine's Day monopole ever since. Cabrera was scrupulous about it, publishing the result as a single unexplained event rather than a discovery. And that is what it has remained. He ran larger detectors afterwards and saw nothing. Other groups built detectors with far more collecting area and saw nothing. The event has never been repeated and has never been convincingly explained away either. It sits in the literature as one data point, 40-odd years old, that either was the only monopole any human has ever detected or was something else entirely. The search continues. There is a dedicated experiment at the Large Hadron Collider looking for monopoles produced in collisions. Certain theories that attempt to unify the forces predict monopoles unavoidably, though at masses so enormous that no accelerator humans could build would ever make one. Some cosmologists argue that the early universe should have produced them in abundance, and that the reason we do not see any is that a period of extremely rapid expansion diluted them to roughly zero per observable universe. That is a real argument, taken seriously, and it means one of the central ideas in modern cosmology exists partly to explain something that is not there. So here is where we stand, 4 steps into the chain. The picture of magnetism you have carried since childhood is a picture of interference. The lines in it are a bookkeeping device with no physical count, and the equations that describe it contain, in their second line, an open admission that magnetism is missing something that electricity has, with no reason given. None of that touches the original question, though. We still have not said what the field is, or why moving charge makes one, and the answer to that second question is going to be the strangest thing you hear tonight, because it turns out that whether there is a magnetic field at all depends on how fast you happen to be walking. In 1905, a 26-year-old patent clerk in Bern published a paper that rebuilt space and time, and he opened it by talking about a magnet. Not about clocks, not about trains, not about the speed of light. The very first paragraph of the paper that gave us special relativity, a paper titled, unglamorously, On the Electrodynamics of Moving Bodies, begins with an observation about a magnet and a coil of wire. And it begins there because that is where Albert Einstein's problem actually came from. He was not primarily trying to fix the behavior of light. He was trying to fix an embarrassment in the theory of magnetism. Here is the embarrassment, and I want to lay it out carefully, because once you see it, you cannot stop seeing it. Take a coil of wire connected to a meter and a bar magnet. Hold the coil still and push the magnet toward it. A current flows, the needle moves. The explanation, in the physics of 1895, is Faraday's law. The magnetic field through the coil is changing, and a changing magnetic field creates an electric field, and that electric field pushes the electrons around the loop. Perfectly clear. Now do it the other way. Hold the magnet still and push the coil toward it, at the same speed. The needle moves by exactly the same amount. The current is identical. But the explanation given at the time was completely different. Now the magnetic field is not changing at all, so there is no induced electric field. Instead, the charges in the wire are moving through a static magnetic field, and moving charges in a magnetic field feel a sideways force. Different cause, different mechanism, same measurable result, every time, to any precision anyone could measure. Einstein's opening sentence says, in effect, that this is not acceptable. The physical situation is one situation. There is a magnet and a coil, and they are approaching each other. Which of them you call moving is a matter of where you decided to stand. And a theory in which the cause of an effect depends on an arbitrary choice of viewpoint, while the effect itself does not, is a theory that has something wrong with it. Fixing that required abandoning absolute time, and what fell out the other side is the reframing I want to give you now, because it is the single most useful thing anyone has ever said about what magnetism is. The magnetic field is not a separate thing from the electric field. There is one field, the electromagnetic field, and how much of it looks electric and how much of it looks magnetic depends entirely on how you are moving. Two observers passing each other will disagree, genuinely and irreconcilably, about the strength and even the existence of a magnetic field in a given region. They will agree completely about the force on any given particle. The split into electric and magnetic is a property of the observer, not of the universe. That is a large claim, so let me make it concrete, and let me use a wire, because the numbers in a wire are the most astonishing part of the whole story. There is a copper wire in the wall behind you. When a current runs through it, we say electrons flow through the metal. Ask most people how fast, and they will guess something close to the speed of light, because the light comes on instantly when you flip a switch. That is not what happens. The signal travels near light speed, the way a pressure wave travels down a pipe already full of water. The electrons themselves barely move. In a typical household wire, carrying a typical current, the average drift speed of the conduction electrons is on the order of 1/10 of a millimeter per second. Slower than a garden snail. Slower than the minute hand of a wall clock sweeping across its face. An electron that leaves your fuse box heading for a lamp would take several hours to arrive. I want to sit inside that wire with you for a moment. Shrink down. You are inside the copper, and around you is a rigid three-dimensional lattice of positive metal ions, locked in place, vibrating slightly with heat. Between them drifts a sea of electrons, and in the direction of the current they are creeping, 1/10 of a millimeter in a second, an ambling, almost stationary shuffle. From where you stand, the lattice is still, and the electrons are barely moving, and the wire as a whole is electrically neutral, as much positive charge as negative, everywhere, so a stray charged particle sitting outside the wire feels no electrical pull at all. If that particle is itself moving, though, it gets shoved sideways. We call the thing doing the shoving a magnetic field. Now change your state of motion. Start drifting along with the electrons, matching their absurd crawl exactly. Nothing physical has changed. You have simply chosen to walk at the speed of a snail. But from here, the electrons are at rest, and it is the positive lattice that is streaming past you. And in relativity, a moving arrangement of objects is contracted along the direction of its motion. The spacing between those positive ions is now very slightly smaller than it was. There are, from your point of view, slightly more positive charges per centimeter of wire than there are negative ones. The wire is no longer electrically neutral in this frame. It has a net positive charge density, and that stray particle outside, which in the first frame was being pushed by something we called magnetism, is now being pulled by a plain electrostatic attraction toward a wire that has become positively charged. There is no magnetic explanation needed. Same particle, same force, same measured acceleration, different story. That is what magnetism is. It is what electricity looks like when the charges are moving relative to you. Now for the part that makes this genuinely hard to believe, which is the size of the correction. At a drift speed of 1/10 of a millimeter per second, the relativistic contraction is not small. It is preposterous. The fractional change in length is roughly 1 part in 10 to the 26th power. Write out a 1, put 26 zeros after it, and the effect is 1 over that. There is no instrument on Earth, and no instrument anyone can imagine, that could detect a length change that small directly. And yet it runs the washing machine. It works because of what that tiny correction is a correction to. The electric force between charges is not merely strong. Between two protons, the electromagnetic repulsion is roughly 10 to the 36th times stronger than the gravitational attraction between them. That is a 1 with 36 zeros after it. Gravity holds galaxies together, and it is that much weaker than the force we are talking about. When you take a force of that magnitude and apply a correction of 1 part in 10 to the 26th, what is left over is still enormous. It is enough to spin a motor. It is enough to lift a car in a scrapyard. It is enough to hold a photograph to a refrigerator against the pull of an entire planet. Every magnetic effect you have ever seen is a relativistic residue. Every electric motor is running on the fact that time and space behave differently for things in relative motion, and the electrons responsible are moving slower than you could crawl. There is an obvious objection to all of this, and it is worth answering because the answer sharpens the point. If relativity is doing this much work at snail speeds, why does nothing else in daily life show relativistic effects? Why can you throw a ball or drive a car without space contracting in any way you notice? The answer is that ordinary matter is electrically balanced almost perfectly. Every object around you contains almost unimaginable quantities of positive and negative charge, in amounts so nearly equal that the leftover is effectively nothing. A wire carrying current is different in one specific respect. The negative charges are moving, and the positive ones are not. That separation of motion is what lets a relativistic correction survive at all, because it applies to one population and not the other, and it is applied to a cancellation so exact that a residue of 1 part in 10 to the 26th is still a force you can feel. If you could somehow strip 1% of the electrons out of a person and 1% out of another person standing a meter away, the electrical repulsion between them would be comparable to the weight of a mountain range. That is the scale of the cancellation we live inside. Magnetism is what leaks through a crack in it. I said earlier that this reframing is the most useful thing anyone has said about magnetism, and I meant it, but I want to be honest about what it does and does not accomplish. It does not answer the child's question. What it does is reduce two mysteries to one. You no longer have to ask what electricity is and separately what magnetism is. There is one field, and magnetism is a viewing angle on it. But now the whole weight of the question rests on the electromagnetic field itself. What is it? Not what does it do. We have 4 equations for that, and they are flawless. What is it made of? What is the stuff whose viewing angles we have been arguing about? Maxwell tried to answer that and failed. He built mechanical models, an invisible medium filled with spinning cells and rolling particles, an elaborate clockwork filling all of space, and every one of them was abandoned. The equations survived. The machinery did not. Einstein removed the last of it by showing that the medium was unnecessary and undetectable. What is left is a field, a thing that has a value at every point in space, that carries energy and momentum, that ripples at a fixed speed, and that is not made of anything else. There is your flaw again, one level lower than where we found it at the start of the night. Charge exists. The field exists. Because it does. Except that we are not quite done, because there is one more thing in a magnet that has nothing to do with charges moving through wires. Something inside an iron atom is producing a magnetic field while sitting perfectly still. And when physicists went looking for what was moving in there, they found something that has angular momentum without rotating, and they found it because of a badly paid man with a very cheap cigar. It is February of 1922, in a laboratory in Frankfurt, and Stern-Gerlach is holding a glass plate up to the light and finding nothing on it. The apparatus behind him has taken months to build and is close to the limit of what the equipment of the period could do. A small oven inside a vacuum chamber has been heating silver until it evaporates. The vapor escapes through a pinhole, passes through a narrow slit, and emerges as a thin ribbon of silver atoms traveling in a straight line through empty space. Between the slit and the far wall, the beam passes through a magnet with deliberately mismatched pole pieces, one shaped to a knife edge, the other hollowed out, so that the magnetic field between them is not uniform. It is stronger near the sharp edge and weaker near the hollow. That asymmetry is the whole point. A uniform field would only twist a magnetic atom. A field that varies across space will actually pull it to one side. At the far end, the silver lands on a glass plate and builds up an invisibly thin deposit, and after hours of running, the plate is removed and examined. Tonight, there is nothing on it. Gerlach leans over it in the lamplight and sees clear glass. He is not a wealthy man. He is a junior physicist on a poor salary in a country whose currency is beginning to come apart, and he smokes cheap cigars, the kind made from low-grade leaf with a high sulfur content. He breathes over the plate as he examines it, and the sulfur in his breath reaches the silver, and silver sulfide is black, and as he watches, a dark line develops, out of nowhere on the glass, the way a photograph comes up in a tray. The line is there, and it is not one line. It has split cleanly into two, with a gap between them and nothing at all in the middle. That gap is one of the most important empty spaces in the history of science, and I want to explain why. Classically, each silver atom acts like a tiny magnet pointed in some random direction. As the atoms come out of the oven, those directions should be scattered evenly across every possible orientation. Passing through the uneven field, an atom pointed one way gets pulled hard toward the sharp pole. An atom pointed the opposite way gets pushed the other direction, and everything in between gets deflected by an amount somewhere in the middle. The prediction is a smeared band, densest in the center, fading out at the edges. What appeared was two spots, not a band, two, which means the atoms were not pointed in every possible direction. Every single silver atom coming out of that oven was aligned either fully with the field or fully against it, and nothing else was permitted. Orientation in space, it turns out, is not continuous. Angular momentum comes in discrete allowed values, and there is nothing in between them. Gerlach and Otto Stern sent a postcard of the result to Niels Bohr. It is one of the founding images of quantum mechanics, and it was developed by a bad cigar. A few details make the achievement larger than it first sounds. The separation between the two spots was a fraction of a millimeter. The beam had to travel through a carefully shaped field for a considerable distance to spread that far, and the whole apparatus had to hold a vacuum and a stable magnet alignment for hours, while a barely detectable quantity of silver accumulated. Stern had been arguing for the experiment for years and had trouble getting it funded. At one point, the work was kept going with money raised from outside the university. Stern received the Nobel Prize in 1943, largely for this line of work. Gerlach, who built the magnet and developed the plate, never did. There is also a lovely irony in the result, which physicists only appreciated later. The two-spot pattern was taken at the time as confirmation of an older model of the atom that was on its way out, and the agreement was partly a coincidence of two errors cancelling. The experiment was right. The reasoning that predicted it was wrong. What the silver atoms were actually revealing was not the orbit of an electron around a nucleus, but something much more fundamental in the electron itself, and it took 3 more years for anyone to say so. 3 years later, in 1925, 2 graduate students in Leiden worked out what the two spots meant. Samuel Goudsmit and George Uhlenbeck proposed that the electron carries its own angular momentum, built in, not from orbiting anything, an intrinsic spin, with exactly 2 allowed orientations relative to any direction you choose to measure. It explained the silver beam. It explained a whole family of puzzles in atomic spectra, and it was, as a physical picture, immediately impossible. Hendrik Lorentz did the arithmetic for them. and it was not kind. If the electron were a small charged sphere, physically rotating fast enough to produce the observed angular momentum, then given any size consistent with what was known, the surface of that sphere would have to be moving many times faster than light. Modern experiments have made this far worse. We now know the electron is smaller than about 10 to the minus 18th of a meter, if it has any size at all, which nothing suggests it does, and at that size, the required surface speed is absurd by an enormous factor. There is no version of this in which something is rotating. There is a story attached to this that I think about often. Ralph Kronig had exactly the same idea several months before Goudsmit and Uhlenbeck did. He showed it to Wolfgang Pauli, who told him it was clever but had nothing to do with reality, and Kronig, being young and being confronted by Pauli, dropped it and never published. Pauli later accepted spin completely and did much of the work of formalizing it. Kronig had been first and had let himself be talked out of it, and that is the kind of thing that happens in science more often than the tidy version admits. So what is spin, if nothing is spinning? The honest answer is that spin is an intrinsic property of the electron, in exactly the same category as its mass and its charge. It is a quantity the particle has, which behaves mathematically like angular momentum. It adds like angular momentum. It is conserved like angular momentum. It responds to magnetic fields like angular momentum, and which has no underlying motion producing it. The word is a historical accident that has never been corrected. There is no smaller picture beneath it. Ask what is doing the spinning, and the answer is, nothing is spinning. And this is the thing that makes your refrigerator magnet work. The magnetic field of a bar magnet does not come primarily from electrons orbiting nuclei. It comes overwhelmingly from electron spin, from an intrinsic magnetic moment attached to a point-like particle for no reason anyone can give. Now I want to show you the strangest juxtaposition in physics. In 1928, Paul Dirac wrote down an equation combining quantum mechanics with special relativity, and out of it, unrequested, came the electron's magnetic moment, and specifically, a number called the G factor, which the equation said should be exactly 2. A naive classical calculation gives 1. Dirac's equation gave 2, and measurements agreed, and it was one of the great early triumphs of the theory. Then better measurements found that it is not exactly 2, it is very slightly more. Julian Schwinger calculated the leading correction in 1948, and it came out to a remarkably compact expression. The fine structure constant, divided by 2 times pi, roughly 1 part in 1,000. That expression is carved on Schwinger's gravestone. Since then, both sides of the comparison have been pushed to their limits. The theoretical prediction now includes contributions from thousands of separate quantum processes. The experimental measurement, in its most refined form, published in 2022, gives the value 1.00115965218059, with an uncertainty of about 1/10 of a part per trillion. The two numbers agree to roughly 12 significant figures. It is worth saying where that small excess above 2 actually comes from, because it is the clearest window we have into what the modern theory thinks a magnetic field is. In quantum electrodynamics, an electron is never simply an electron sitting alone. It is continually emitting and reabsorbing disturbances in the electromagnetic field, particles of light that exist too briefly to be caught, and which in turn can become pairs of particles that annihilate again. The electron is surrounded by a cloud of this activity, and the cloud changes how it responds to an external field. Schwinger's correction is the contribution of the simplest such process. Later terms add processes of increasing complexity, and each contributes less than the last, because each carries another factor of the fine structure constant, that famous number close to 1/137, which measures how strongly light and matter are coupled. The series converges because that number is small. If it were larger, None of this would be calculable, and the theory that gives us 12 decimal places would give us nothing at all. There is nothing else in science tested to that standard. Nothing in chemistry, nothing in biology, nothing in astronomy, nothing anywhere. If you measured the distance from here to the moon with the same fractional precision, your error would be smaller than the width of a human hair. Quantum electrodynamics can tell you the magnetic strength of a single electron more accurately than we can measure almost anything else in the universe. And it cannot tell you what has the strength. It cannot tell you why a point with no size and no internal structure and nothing rotating inside it should be a magnet at all. It computes the number to 12 digits for a property whose existence it simply assumes. That is the shape of this whole subject in a single comparison. Description, perfect. Explanation, absent. We know exactly how magnetic an electron is, and not the first thing about why it is magnetic. Hold on to that, because we now have one more step to take before the floor really gives way, and it is the step nobody teaches. So far we have talked about individual electrons, but a magnet is not one electron. It is something like 10 to the 23rd of them, and they have to agree with each other. And getting that many things to agree is a completely separate problem. A problem so severe that there is a theorem, proved twice, stating that in the physics most people believe in, the object on your refrigerator door cannot exist. In 1911, a 25-year-old Danish student named Niels Bohr submitted a doctoral dissertation on the electron theory of metals, and buried inside it was a proof that magnets cannot exist. He does not appear to have made much of it. The thesis was written in Danish, was not widely read, and Bohr went on within 2 years to do work that made him one of the most famous scientists alive. 8 years later, in 1919, a Dutch physicist named Hendrika Johanna van Leeuwen proved the same theorem independently in her own doctoral work at Leiden, apparently without knowing Bohr had already done it. The result now carries both their names, and it is one of the most quietly devastating statements in physics. Here is what it says. Take any collection of charged particles, as many as you like, arranged however you like, interacting however you like. Treat them with classical physics, Newton's laws for the motion, Maxwell's equations for the fields, ordinary statistical mechanics for the temperature. Let the whole system settle into thermal equilibrium. Now apply a magnetic field and ask what the net magnetization of that system is. The answer is 0. Not small, not negligible. Exactly 0, identically, for every possible arrangement of matter, at every temperature, in every field strength. The proof is short, and while I will not walk you through the mathematics, I can tell you its shape, because the shape is what makes it so hard to escape. In classical statistical mechanics, everything you can measure about a system in equilibrium is derived from a single quantity that sums over all the possible states the system can occupy. The magnetic field enters that sum in exactly one place, and it enters in such a way that a simple change of variable, a relabeling essentially, removes it entirely. The total comes out identical whether the field is on or off, and since magnetization is defined as how the system's energy responds to the field, and the response is exactly nothing, the magnetization is exactly nothing. There is no loophole in it. You cannot fix it with a cleverer material, or a stronger field, or a lower temperature. In a universe running on classical physics, there are no permanent magnets. There is no attraction of iron to lodestone. There is no compass. Diamagnetism does not exist. Paramagnetism does not exist. Ferromagnetism does not exist. The entire subject we have spent the night on would have nothing in it. Now think about where you probably are right now, and think about what is stuck to your refrigerator door. That object is a macroscopic quantum mechanical effect, not a subtle one, not one that requires a particle accelerator or a dilution refrigerator, or a laser to detect. It is at hand height, in a kitchen, in essentially every home on this planet, and it is doing something that is flatly impossible under the physics that most people carry around in their heads as a description of how the world works. Quantum mechanics is usually presented as a set of rules governing things too small to see, safely quarantined from ordinary life. It is not quarantined. It is holding up a photograph. So what actually does it? The correct answer came in 1928 from Werner Heisenberg and independently from Paul Dirac, and it is called the exchange interaction. And the first thing to say about it is that it is not magnetic. Think about what has to happen for a piece of iron to be a magnet. Every iron atom has a magnetic moment, from the spins of a few of its electrons. In an ordinary material, those moments point in random directions and add up to nothing. In iron, over regions containing enormous numbers of atoms, they all point the same way. Something has to be making them agree. The obvious candidate is that each little atomic magnet feels the field of its neighbors and lines up with them. That is what magnets do, after all. But run the numbers, and the idea collapses instantly. The energy of interaction between two neighboring atomic magnetic moments in a solid is around 1/10,000th of an electron volt, which corresponds to a temperature of a few degrees above absolute zero. Above that temperature, thermal jostling would tear the alignment apart. Iron holds its magnetization up to 1043 Kelvin, 770 degrees Celsius, hot enough to glow. The magnetic interaction is too weak by a factor of roughly 1,000. It cannot possibly be the cause. What actually holds them in line is the Pauli exclusion principle, and I want to say this slowly because it is one of the most beautiful pieces of reasoning in solid-state physics. Electrons are identical to one another in a very strict sense, and they obey a rule forbidding any two of them from occupying the same quantum state. One consequence of that rule is that two electrons whose spins point the same way are more strongly forbidden from being in the same place than two electrons whose spins point in opposite directions. Same spin electrons keep their distance from each other automatically, not because anything pushes them apart, but because the mathematics of identical particles will not permit them to overlap. Now, electrons repel each other electrically, and that repulsion costs energy. If a pair of electrons is forced to stay further apart, the electrical energy of the arrangement goes down. So in the right kind of atomic lattice, and the spacing and the shape of the electron orbitals both have to be right, which is why this is so rare. The state where neighboring spins point the same way is genuinely lower in energy than the state where they point opposite. The material falls into alignment because alignment is cheaper. Read that again, because it is the punchline of the entire first half of tonight. The force holding the note to your refrigerator door is electrical, not magnetic. The alignment that produces it is caused by electrons refusing to share a state. Ferromagnetism is electrostatics wearing a costume borrowed from quantum statistics, and the costume is so convincing that it took humanity until 1928 to see through it. The rarity is worth pausing on. Of all the naturally occurring elements, only a handful are ferromagnetic at ordinary temperatures. Iron holds out to 1043 Kelvin. Cobalt holds to 1394. Nickel gives up at 631. And gadolinium, the fourth, loses its ferromagnetism at 292 Kelvin, 19 degrees Celsius. Gadolinium is a metal that stops being a magnet if you hold it in your hand on a warm day. Out of 90-odd elements, that is nearly the whole list. And this planet happens to have a core made mostly of the first one. Above the critical temperature, the Curie point, named for Pierre Curie, who established the law in his doctoral thesis in 1895, the alignment does not weaken gradually and then stop. It undergoes a phase transition, as sharp in its way as ice becoming water, and the magnetism vanishes. Below it, the material does something else clever. In 1899, and again in 1907, Pierre Ernest Weiss worked out why a piece of iron can sit in a drawer without being a magnet, even though its electrons are all locked into alignment. The iron divides itself into domains, regions typically a few thousandths of a millimeter across, each one fully magnetized, but pointing in different directions so that the whole cancels. Magnetizing a piece of iron does not create the alignment. The alignment was already there. What you are doing is persuading the domains to agree with each other. And this is where I want to give you something you can actually do, because magnetism is invisible, but this part is not. Wrap a few hundred turns of thin wire around an iron nail. Connect the ends to an amplifier and a speaker, the sort of thing a hobbyist can assemble in an afternoon. Now take an ordinary magnet and move it slowly toward the nail. Not quickly. Creep it in, a millimeter at a time. You will hear a sound. It is not a hum, and it is not a tone. It is a rush of irregular clicks and crackles, like rain starting on a roof, or like sand poured onto paper. Each individual click is a domain wall inside the nail, tearing free of a defect in the crystal and jumping to the next one. The wall does not glide. It sticks, strains, and lets go, and every letting go induces a tiny pulse of current in your coil that the speaker turns into a click. Heinrich Barkhausen discovered this in 1919, and it means something quite large. Magnetization is not smooth. It is granular and lumpy and full of discrete jumps, and the graininess is coming from the arrangement of atoms in a crystal lattice responding to a quantum rule about identity. What is coming out of that speaker is the sound of electrons declining to share a state, played through a loudspeaker in your kitchen in real time. You cannot see a magnetic field. You cannot feel one. But you can listen to a piece of iron becoming a magnet, and it sounds like rain. Two more consequences of all this are worth a moment, because they show how far the same physics reaches. The first is that the strongest permanent magnets in the world are recent inventions. Neodymium magnets, the small silver discs that are startlingly difficult to pull apart, were developed independently in 1982 by a team in Japan and a team at an American car company, and they work by combining ions exchange coupling with a rare earth element that locks the alignment stubbornly to one direction in the crystal. A neodymium magnet, a centimeter across, produces a field roughly 20,000 times stronger than the magnetic field of this entire planet. The second is that every material in the world is magnetic, very slightly, in the opposite sense. Put anything in a magnetic field, and the field induces circulating currents in its electrons that oppose it, an effect called diamagnetism, and it is universal. It is normally far too weak to notice. In 1997, in a laboratory in the Netherlands, two physicists put a live frog inside a 16 Tesla magnet, and the frog floated in mid-air, held up by the diamagnetic repulsion of the water in its own body. The frog was unharmed. One of the two physicists, André Geim, won an Ig Nobel Prize for it in 2000, and a decade later won an actual Nobel Prize for something else entirely. You are diamagnetic too. In a strong enough field, you would float. So let me put down where we have arrived, because we are about to change scale entirely. Let me step back for a moment and put the pieces we have together, because we are roughly halfway and the ground has shifted several times. We started with a question a child could ask and found that it has no last step. We watched 2,000 years of people using magnetism perfectly while explaining it not at all. We watched a compass needle twitch in Copenhagen and merge two forces into one. We found out that the famous picture of the field is a picture of interference, and that the equations describing it contain an open admission that something is missing. We learned that magnetism is what electricity looks like from a moving frame, produced by electrons drifting slower than a snail. We met a particle with angular momentum and nothing rotating, measured to 12 decimal places and unexplained at the first. And we found a theorem stating that in the physics most people believe in, none of this could happen at all. That a refrigerator magnet is a piece of quantum mechanics you can pick up with 2 fingers. Every one of those steps made the description better and left the original question exactly where it was. Now I want to take the same question and make it very large, because the biggest magnet in your life is not on your refrigerator. You are standing on it. Beneath your feet, at a depth of about 2,900 kilometers, the rocky part of this planet ends and something else begins. From there, down to a radius of about 1,220 kilometers from the center, there is a shell of liquid metal, roughly 2,260 kilometers thick, mostly iron, with nickel and some lighter elements mixed in, at temperatures somewhere between 4,000 and 5,400 Kelvin. Below that is the inner core, solid iron and nickel, held rigid not by cold but by pressure, at something like 5,400 Kelvin, which is close to the surface temperature of the Sun. That arrangement generates a magnetic field that reaches tens of thousands of kilometers out into space, and it is why a compass works. But look at those temperatures again, because there is a problem sitting in them that ought to stop the story dead. Iron stops being a magnet at 1,043 Kelvin. We established that in the last part. Above the Curie point, the thermal jostling overwhelms the exchange alignment, and the ferromagnetism vanishes in a sharp transition. The outer core is 4 to 5 times hotter than that. If you could lower a bar magnet into Earth's core, it would be thoroughly demagnetized long before it got anywhere near melting. So the planet is magnetic, and the planet contains nothing that is capable of being magnetized. Not 1 gram of the material down there can hold a magnetic alignment at those temperatures. And yet the field is there. It is strong. It has been there for billions of years, and it is the reason this world still has an atmosphere. The resolution is that Earth's magnetism is not stored. It is generated, continuously, and it has to be, because the moment the generating stopped, the field would begin decaying away. Estimates of how long the field would last if the machinery switched off tonight come out at something like 20 to 50,000 years. On the timescale of the planet, that is nothing. Everything you know about the compass depends on a process that is running right now, underneath you, and that has not been allowed to pause since before there were continents. The process is called a dynamo, and the underlying principle is the same one Faraday found with his iron ring. Move a conductor through a magnetic field, and you generate currents. Currents generate magnetic fields. If the geometry of the motion is right, the field the currents generate can reinforce the field that produced them, and the whole arrangement becomes self-sustaining, feeding itself, amplifying itself, running as long as something keeps the fluid moving. Something does keep it moving. 2 things, in fact. The first is heat. The core is still cooling from its formation, and heat escaping upward drives convection in the liquid metal the way heat drives circulation in a pot of water on a stove. The second is subtler and probably more important. As the planet cools, iron freezes onto the solid inner core, and as it freezes, it rejects lighter elements into the liquid above. That light material is buoyant and rises, stirring the fluid from below in a slow, continuous churn. The inner core is growing, and its growth is helping to power the field. Then rotation gets involved. Earth turns once a day, and in a rotating fluid, the Coriolis effect organizes what would otherwise be a chaotic churn into long columns aligned roughly with the axis of spin. The convection stops being a random boil and becomes a set of twisted, helical rollers. That organization is what allows the flow to stretch and fold magnetic field lines systematically, rather than tangling them into noise. It is also why the magnetic axis stays anywhere near the rotational axis instead of wandering freely. Whether a dynamo runs at all comes down to a competition, measured by a quantity called the magnetic Reynolds number, the rate at which the flow stretches field lines against the rate at which electrical resistance lets them slip and decay. Below a threshold of somewhere between 10 and 100, depending on the geometry, the field always dies. Above it, the field can grow. Earth's outer core is comfortably above the threshold by a wide margin. The idea has a difficult history. Joseph Larmor proposed self-exciting dynamos in 1919, thinking about sunspots. Then in 1933, Thomas Cowling proved a theorem that very nearly killed the whole field. No perfectly axially symmetric flow can sustain a magnetic field, since the obvious thing a rotating planet does is behave symmetrically about its axis. This looked fatal, and for the better part of 2 decades, the geodynamo was regarded as a dead end. It was rescued by Walter L. Sasser and Edward Bullard in the 1940s and 50s, who showed that real convection is not axially symmetric. The columns break the symmetry, and that asymmetric flows can and do sustain fields. Even so, nobody could demonstrate it. The equations are brutally nonlinear, and the parameters of a planetary core are far outside what any computer could handle. Then, in 1995, Gary Glatzmeyer and Paul Roberts published the first fully self-consistent, 3-dimensional simulation of a geodynamo. It ran on the equivalent of tens of thousands of simulated years, and it produced a field with roughly the right strength and roughly the right geometry. And then, without being asked, it flipped. Somewhere in the run, the simulated magnetic field reversed direction entirely. North became south, for reasons that emerged from the fluid dynamics rather than from anything anyone had put in by hand. Nobody had programmed a reversal. The machinery did it on its own. That was the theory. The experiment came 4 years later, in a warehouse in Latvia. A team led by Agris Gailaitis built a facility containing about 2 cubic meters of liquid sodium, a metal chosen because it melts at a low temperature and conducts electricity extraordinarily well, and drove it with a propeller into a helical flow reaching roughly 15 meters per second. In November of 1999, the field inside the apparatus began to grow on its own. Not because they applied one, it grew out of the ambient field in the room, including the field of the planet itself, and it kept growing until losses balanced the amplification. A German team at Karlsruhe achieved the same thing the same year, with a different flow geometry. Then, at Cadarache in France, an experiment called the von Karman Sodium Project stirred about 150 liters of liquid sodium with 2 counter-rotating impellers, and from 2006 onward, it produced not only a self-sustaining field, but spontaneous reversals of its direction. Irregular, unpredictable, and statistically not unlike what the rocks record for this planet. And at the University of Maryland, a 3-meter sphere holding something like 12 tons of liquid sodium spins to probe the turbulent regime a real core lives in. Human beings have built a planetary magnetic field in a room and watched it flip. Which brings us to the thing nobody can answer, and it is the same thing we have been running into all night, just wearing a different costume. A dynamo amplifies a field. It sustains a field. It does not create a field out of nothing. The equations are perfectly clear about this. If you start with exactly 0 magnetic field everywhere, a dynamo produces exactly 0 forever. There has to have been a seed, some pre-existing field, however faint, for the churning core to grab hold of and grow. So where did Earth's seed field come from? There are candidates. The young sun was magnetically far more active than it is today, and the disk of gas and dust the planets formed from was threaded with fields. There is a mechanism proposed by Ludwig Biermann in 1950 by which a plasma with mismatched temperature and density gradients generates a magnetic field from an unmagnetized state. the leading explanation for the extremely faint fields that seem to pervade intergalactic space. And there were fields already present in the interstellar material this solar system condensed out of. Any of those would be sufficient. Almost anything would be sufficient, because a dynamo can amplify a field by many orders of magnitude. But sufficient is not the same as known, and there is no way to go back and check. The oldest direct evidence we have comes from magnetized crystals in ancient Australian rock, which some researchers read as recording a field more than 3 billion years ago and possibly over 4, and whose reliability is actively argued over. So the honest position is this. We know the planet's field is generated rather than stored. We know the mechanism, we have simulated it, and we have built working versions of it in laboratories. And we do not know where the first field came from. The chain of explanation goes down beautifully, level by level, and then arrives at a beginning nobody can account for, and stops. You have heard that sentence before tonight. At a completely different scale, about a completely different object. The flaw is in the same place. It is just further down. I want to start this part with a fact that reliably breaks people, and it is not a trick. Earth's magnetic North Pole is, physically, a magnetic South Pole. Here is why, and it is completely unavoidable once you accept the definitions. The end of a compass needle that points north is, by definition, the needle's north pole. That is what North Pole means for a magnet, the end that seeks north. Now, opposite poles attract, and like poles repel. That is the first thing anyone learns about magnets. So if the needle's north pole is being attracted toward the top of the planet, then whatever is up there must be a magnetic south pole. There is no error hidden in that. The naming convention was fixed by navigators centuries before anyone understood what a magnet was, and by the time physicists arrived with a proper definition of polarity, the sailors' names were far too entrenched to change. So the geographic Arctic contains a magnetic south pole, and the Antarctic contains a magnetic north pole, and every physics textbook quietly carries the contradiction in a footnote. That is the first thing that is not quite right about the compass. Here is the second. It does not point at the geographic pole either. Shen Kuo noticed this in the 11th century and wrote it down without explanation. The magnetic axis of this planet is tilted about 11 degrees away from the axis it spins on. Ask why 11, and there is no first principles answer. Simulations produce a tilt of roughly that size as a natural consequence of turbulent, non-symmetric convection in a rotating fluid. The columns organize near the spin axis, but never perfectly on it. But no theory tells you the number in advance. It is what the fluid happens to be doing, and it does not stay put. The magnetic pole wanders, and in the last few decades it has been in a hurry. James Clark Ross located the northern magnetic pole in 1831 on the Boothia Peninsula in Arctic Canada. Through most of the 20th century, it drifted at something like 15 kilometers a year. Noticeable, but a curiosity for cartographers. Then, in the 1990s, it accelerated sharply, reaching speeds of 50 to 60 kilometers a year. It left Canadian territory, crossed the international dateline around 2017, and headed toward Siberia. That acceleration had a practical consequence. The World Magnetic Model is the mathematical description of Earth's field used by aircraft navigation, marine navigation, and the compass application in every smartphone on the planet. It is updated on a 5-year schedule. The pole was moving fast enough that by 2018 the model had drifted out of specification early, and an unscheduled emergency update had to be issued in February of 2019. The planet's magnetic field moved faster than the paperwork. Now for the larger version of the same instability. The field does not merely wander, it flips. We know this because of a piece of natural bookkeeping that is very hard to argue with. When lava erupts and cools, The magnetic minerals in it are free to align with the surrounding field while the rock is still hot, and then they are locked in place as it drops below the Curie temperature. Every lava flow is a frozen compass reading, dated by the rock around it. Sedimentary layers do a slower version of the same thing as magnetic grains settle out of water. In 1906, a French scientist named Bernard Brunhes examined volcanic rock in central France and found that it was magnetized backwards, pointing the wrong way entirely. The obvious response was that something had happened to that particular rock. Then, in 1929, Motonori Matuyama in Japan showed that the reversed rocks were systematically older than the normal ones. Everywhere he looked. It was not the rocks, it was the planet. The last complete reversal happened about 780,000 years ago. That is recent enough that our own genus was already walking around and using tools. There were people, of a kind, alive on Earth when the compass direction changed. Before that, the record runs backward through hundreds of reversals, and their timing is wildly irregular. Over the last few million years, the average interval has been in the region of 200,000 to 300,000 years. But averages are misleading here. Some intervals are a few tens of thousands of years, and in the middle of the Cretaceous, the field stayed put for something like 40 million years without a single reversal, a period so long and so strange that it has its own name. There are also events that are not quite reversals. About 41,000 years ago, during what is called the Lachamp excursion, the field weakened dramatically, dropping to something like 5% of its present strength, flipped for a few hundred years, and then came back to where it had started. The strength of the field, in other words, is not guaranteed even between reversals. Which brings us to a claim you will find all over the internet, and which deserves a proper answer rather than a dismissal. Since Gauss made the first absolute measurements in the 1830s, the strength of Earth's dipole field has been declining, by something in the range of 5 to 9% per century. That is a real, measured, uncontroversial trend, and it is the factual seed of a great deal of alarming material. The reasoning goes, the field is weakening, reversals happen when the field weakens, therefore a reversal is imminent, therefore catastrophe. Here is what the data actually support. The current strength of the field is still above the average value for the last few million years. The planet has been in an unusually strong phase, and part of what we are watching may simply be a return toward normal. Declines of this size have happened repeatedly in the record, without a reversal following them. Transitions in the rock take somewhere between 1,000 and 20,000 years, which means that even if one has begun, no individual would experience it as an event. And during a transition, the field does not switch off. It becomes disorganized and multipolar, several weaker poles scattered around the planet, rather than a clean north and south, while retaining a substantial fraction of its strength. The real consequences of a weakening field are serious and unglamorous. More radiation reaching satellites, more disruption to navigation systems, more vulnerability in power grids. Those are infrastructure problems. They are not the end of the world, and the geological record is quite clear that life has come through hundreds of these without any consistent pattern of mass extinction attached. There is one place where the weakening is already concrete. Over the South Atlantic and parts of South America, there is a region where the field is anomalously feeble, around 22,000 nanotesla, where you would expect something like 32,000. It is called the South Atlantic anomaly, and satellites passing through it experience noticeably more radiation. The Hubble Space Telescope suspends some of its observations while transiting the region. European satellite measurements have tracked the anomaly growing over recent decades and, since around 2020, beginning to split into two separate lobes. Nobody is certain what that means. One reading is that it is a patch where the field near the core is locally reversed, and that it may be the early signature of a larger change. Another is that it is a passing feature of a turbulent system. Now let me show you what the absence of all this looks like, because there is a planet next door that ran the experiment. Mars once had a dynamo. We know because a spacecraft mapping the planet in the late 1990s found bands of strongly magnetized crust in the ancient southern highlands, locally reaching 1.5 to 2,000 nanotesla at satellite altitude, magnetization far stronger than anything in Earth's crust. Those bands are fossil field, frozen into rock that cooled while a Martian dynamo was still running. And then, around 4.1 billion years ago, it stopped. The core cooled, or the convection failed, or both. What followed took a very long time and is still happening. Without a global field to deflect it, the solar wind reaches the upper atmosphere directly and strips it away, ion by ion. A spacecraft measuring the loss from 2015 onward found Mars shedding atmosphere at rates around 100 grams per second, rising sharply during solar storms. The surface pressure on Mars today is about 610 pascals, roughly 0.6% of Earth's. There is no shielding worth speaking of. Ultraviolet light reaches the ground unfiltered. I should be careful not to overstate this, because the popular version is too simple. Venus has no global magnetic field either, and it has an atmosphere 90 times denser than ours. Holding on to air depends on gravity and composition, and induced currents in the ionosphere, as well as on a dynamo. But Mars is still the clearest available demonstration that a planet's magnetic field is doing something enormous, quietly, for billions of years. And on this planet, there is exactly one place where you can see it happening. When charged particles from the Sun arrive, most are deflected. Some are funneled along field lines toward the poles and dumped into the upper atmosphere, where they slam into oxygen and nitrogen 100 to 300 kilometers up. The oxygen glows green at one particular wavelength and red at another. Nitrogen contributes the blues and violets. That is the aurora. It is not the field. It is the field's shadow, the visible consequence of an invisible thing doing its work. When the sun sends something larger, the consequences reach the ground. In September of 1859, during what is now called the Carrington event, telegraph systems across Europe and North America failed. Some operators reported shocks, and some lines carried current with their batteries disconnected entirely. Aurorae were reported at tropical latitudes. And on the 13th of March 1989, a geomagnetic storm induced currents in the Hydro-Quebec power grid that brought the entire system down in 92 seconds, leaving about 6 million people without electricity for 9 hours. So this is the shield, generated by a mechanism whose origin nobody can account for, tilted at an angle nobody can derive, drifting fast enough to break the paperwork, weakening at a rate that fuels a small industry of alarm, and visible to human eyes only as colored light in the far north. Which is a good moment to admit something. Every single thing I have told you about this field, we know because of instruments. You are sitting inside it right now. It is passing through your body as you listen, and you cannot feel it at all. Some animals, it appears, can. A European robin weighs about 18 grams. It is smaller than the palm of your hand. It has a brain the size of a peanut, and twice a year, some populations of it cross a continent in the dark, without instruments, without maps, and without ever having made the journey before. For centuries, this was simply accepted as one of those things birds do. Then, in the 1960s, a German researcher named Wolfgang Wiltschko, later joined by Roswitha Wiltschko, with whom he worked for the rest of his career, decided to find out how, and the apparatus he used was almost comically simple. Take a migratory bird during the season when it wants to migrate, and put it in a cage, and it does not settle. It hops, flutters, and repeatedly launches itself toward one particular side of the enclosure, the direction it would be flying if it could. German has a word for this restlessness. Zugunruhe. It is measurable, it is reliable, and it turns a caged bird into an instrument. The cage design that made it quantitative is a shallow cone with an ink pad at the bottom and blotting paper lining the sloping walls. The bird stands in the ink. Every time it tries to take off, it leaves a mark on the paper at the angle it was heading. At the end of a session, you have a paper cone covered in small footprints, densest in one direction, and you can read the bird's intended heading straight off it. Wilczko put robins in cages like these, surrounded them with coils that could generate an artificial magnetic field, and started changing it. And the birds changed direction to match. Rotate the horizontal direction of the field by 90 degrees, and the marks on the paper rotated by 90 degrees. The birds were using the magnetic field of the planet. Then he found the detail that changed everything, and it is a detail nobody would have predicted. He reversed the field's polarity, swapped north for south, while leaving the vertical component alone, and the birds did not care. They kept heading the same way. Then he reversed only the vertical component, leaving the horizontal direction untouched, and the birds turned completely around. That is not how a compass works. A compass responds to polarity, which way is north. The robin was responding to something else, and the something else is called inclination. Picture the field lines of this planet. They emerge from one polar region, arc out and around, and re-enter at the other. Near the magnetic equator, those lines run roughly parallel to the ground. As you travel poleward, they tilt further and further downward, until near the pole they are diving almost vertically into the earth. The angle a field line makes with the horizontal is the inclination, and it changes smoothly with how far poleward you are. A bird reading inclination does not know which way is north in the sense you or I mean. It knows which way is poleward and which way is equatorward, which for a migrating animal is exactly the information required. It also means that such a compass becomes useless at the magnetic equator, where the lines are flat and the poleward direction is ambiguous, a prediction that has been tested and holds up. And because inclination varies with latitude, you can lie to the bird. Set the coils to reproduce the inclination angle found several hundred kilometers away, and a robin sitting in a laboratory in Germany will behave as though it has been relocated, adjusting its intended heading to the journey it now believes it faces. It never left the room, only the angle of a magnetic field changed around it. So the birds are reading the field. The question that took another 40 years was how, and the answer is the reason this part of the story belongs in a video about physics rather than a video about birds. In 1978, Klaus Schulten proposed a mechanism, and in 2000 he and colleagues proposed a specific molecule to carry it out, a light-sensitive protein called cryptochrome found in the retina. The mechanism is called the radical pair mechanism, and here is what it says happens. It is late in the day in a garden in northern Europe. A robin is on a branch, and the light is going blue as the sun drops. A photon of that blue light enters the bird's eye and is absorbed by a molecule inside a cryptochrome protein. The energy knocks an electron loose, and it hops along a chain of anchor points inside the protein, coming to rest some distance from where it started. Now there are two unpaired electrons in the molecule, separated by a few nanometers, a radical pair, and their spins are quantum mechanically correlated, which means the pair as a whole is not in a definite configuration. It exists in a superposition of two arrangements, oscillating between them for a few millionths of a second before the chemistry commits to one outcome or the other. Which outcome it commits to determines which product the reaction makes. Which product it makes determines the signal the cell sends. And the rate of that oscillation, the balance between the two possible arrangements, depends very slightly on the direction of the magnetic field passing through the molecule. So the bird turns its head, The orientation of the protein relative to the planet's field changes, the chemistry shifts by a fraction, and the signal reaching the brain changes with it. The receptor is in the retina, and the signal joins the visual pathway, which means what the robin is very likely experiencing is not a pull or a pressure or an instinctive urge. It is a pattern in what it sees. Pull back and try to imagine it. The bird is looking out over the garden at dusk, and laid across everything, the fence, the hedge, the sky, there is a faint shading, an unevenness of light or contrast that has nothing to do with the sun. It is brightest along one axis and dimmest along another. When the bird turns its head, the pattern sweeps across the scene and settles again. It has been there since the moment the bird opened its eyes on the first day of its life. It is not a symbol, and it is not a needle. It is a directional glow, painted over the world, that says which way is poleward. Now I need to tell you why this should be impossible, because this is the part that makes it physics. The energy involved in tipping an electron's spin, one way or the other, in Earth's magnetic field, is roughly 10 to the minus eighth of an electron volt. The thermal energy sloshing around inside a warm bird at body temperature is about 27 thousandths of an electron volt. The signal is something like 1,000,000 times smaller than the noise it is buried in. By every ordinary accounting, that is the end of the story. You cannot detect a whisper 1,000,000 times quieter than the room. Thermal energy should scramble any alignment the field is trying to impose, instantly and completely. And it does not work, because the field is not trying to impose an alignment. It does not need to move anything or hold anything in place. It only needs to lean, very slightly, on the phase of a quantum superposition during the few microseconds before that superposition collapses into an outcome. The energy required to shift a phase is not the energy required to shift a population. The mechanism survives the noise for exactly one reason, because it is quantum coherent. Read that again. A robin in a hedge is running a coherent quantum spin experiment inside its own eye, continuously, for its entire life, in a warm and wet and violently noisy environment that no laboratory on Earth can reproduce without cryogenic cooling and vibration isolation and a great deal of money. And it is doing it well enough to cross a continent. That claim needs evidence, and the best piece of it came from Oldenburg in 2014. Researchers noticed that robins tested in wooden huts on a university campus could not orient at all. The birds' compasses simply did not work. The same birds, tested in huts screened with grounded aluminium, oriented perfectly well. What the screening removed was electromagnetic noise, weak, broadband radio frequency interference in the range from about 100 kHz to 10 MHz, at amplitudes as low as around 15 nanotesla. That is 1,000th of the strength of the planet's own field. This detail matters more than it sounds. There is no reason for a magnetite compass, or any mechanism based on a physical torque, to be disrupted by such feeble oscillating fields at those particular frequencies. There is a very good reason for a spin-based mechanism to be disrupted by them, because those frequencies are exactly the ones that resonate with electron spin transitions in a field of Earth's strength. The birds are being jammed in precisely the way a quantum spin compass would be jammed, and no other kind would. And in 2021, researchers isolated the specific cryptochrome protein from European robins, studied it in a test tube, and reported that it is magnetically sensitive, and more sensitive than the equivalent protein taken from birds that do not migrate. There is supporting evidence from an unlikely direction as well. Fruit flies can be trained to respond to magnetic fields, and flies engineered to lack their cryptochrome gene lose the ability entirely. Put a human version of the same gene into those flies, and the response comes back. Whatever cryptochrome is doing, it is doing it across a very wide span of the tree of life. in animals separated by hundreds of millions of years. Which raises a question worth sitting with. Cryptochromes are ancient proteins, close relatives of enzymes that repair damage to DNA using light. They were not built to be compasses. They were already present, doing something else entirely, and it appears that the spin chemistry that makes them magnetically sensitive was simply a property they happened to have. Evolution did not design a quantum sensor. It found one lying around and started using it. The physics is demanding too. For the mechanism to work, the two electron spins must stay coherent, must keep their correlation intact, for something on the order of 1 to 100 microseconds. In the warm, crowded interior of a living cell, that is an extraordinarily long time for a quantum state to survive. Physicists spend careers and considerable budgets trying to protect superpositions for comparable durations at temperatures near absolute zero. A bird appears to do it at 40 degrees Celsius, in the dark, while flying. The case is not closed. Nobody has recorded the signal traveling from a cryptochrome molecule to a bird's brain, and the leap from a protein behaving well in a test tube to an animal navigating a continent remains an inference. But the shape of the answer is there, and the shape of the answer is that the quantum mechanics we spent the first half of tonight establishing, spin, superposition, the strange irrelevance of classical intuition, is not confined to laboratories. It is out in a hedge at dusk, in something with feathers, keeping it pointed the right way. The robin's mechanism is not the only one, and the second one is much easier to picture, because it is exactly what you would build if somebody asked you to design a magnetic sense from scratch. You would put a compass needle inside the animal. Some animals have one. In 1975, a graduate student named Richard Blakemore was looking at mud from a salt marsh under a microscope at Woods Hole, and noticed that a population of bacteria in his sample kept accumulating on one particular side of the drop. Not the light side, not the warm side. Always the same geographic direction, no matter how he turned the slide. He brought a magnet near, and the bacteria turned and swam to follow it. Inside those cells, arranged in a neat line, were crystals of magnetite, the same mineral as the lodestones the ancient world found in the ground. Each crystal between 35 and 120 nanometers across. That size range is not an accident. It is precisely the window in which a magnetite crystal is a single magnetic domain, small enough that it does not divide itself up into cancelling regions, large enough that thermal noise cannot flip it. The bacteria are building, with molecular precision, the strongest permanent magnet a crystal that size can be. The chain acts as a needle. It torques the entire cell into alignment with the planet's field, passively, without any sensing or processing at all. The bacterium does not know which way it is pointing. It simply cannot point any other way, and then it swims forward. And there is a lovely detail in why this is useful. These bacteria prefer low oxygen sediment, which means they want to go down. In the northern hemisphere, the field lines tilt downward toward the north, so the northern strains are north-seeking. In the southern hemisphere, the lines tilt downward toward the south, and the southern strains are south-seeking. Both are doing the same thing. Both are using the inclination of the field as a definition of down. Magnetite turns up elsewhere. It has been found in the tissue near the nose of rainbow trout, with nerve fibers that respond when a magnetic field changes. Sea turtles appear to use something more sophisticated still, a map rather than a compass. Kenneth Lohman's group has shown that loggerhead hatchlings placed in a coil system reproducing the field of a specific location along their migratory route will swim in the direction appropriate to that location, as though they know not only which way is poleward, but roughly where on the planet they are, from the combination of inclination and field strength. A study published in 2015 reported that green turtle nesting density along the Florida coast shifted over 2 decades in step with the drift of the local magnetic field, which is a genuinely startling thing to find in a beach survey. Whales are the case that reaches the news, and it needs careful handling. Margaret Klinowska reported in the mid-1980s that British cetacean strandings tended to happen where magnetic contour lines ran perpendicular to the coast, that is, where an animal following a line of constant field strength would swim straight into land. In 1986, Joseph Kirschvink and colleagues analyzed 212 strandings along the American East Coast and found a statistically significant association with local minima in the field. And a study published in 2020 examined 31 years of grey whale strandings and found a correlation with solar activity, but the strongest association was with radio frequency noise from solar events rather than with magnetic disturbance itself, which the authors read as the animal's sense being jammed rather than misled. If you have been paying attention, you will recognize the jamming frequencies from the last part. Now I want to do something that this kind of story usually does not do, and tell you about the cases that did not hold up. Because a channel that only tells you the results that worked is not telling you what science is like. In 2013, a peer-reviewed paper reported that dogs prefer to align their bodies along the north-south axis while defecating. The study was not casual. 70 dogs of 37 breeds, observed over 2 years, across nearly 1,900 defecations and more than 5,000 urinations, with the alignment showing up only during periods when the magnetic field was quiet, about a fifth of daylight hours. It is a careful piece of work, and it became a global news story overnight for obvious reasons. Attempts to replicate it have not consistently reproduced the effect. That does not prove the original was wrong. It does mean the result is not established, and anyone telling you confidently that dogs poop facing north is going considerably beyond what the evidence supports. The same thing happened with cattle. A study in 2008 analyzed satellite images of 8,500 cattle across 308 pastures and reported north-south alignment while grazing. An independent reanalysis 3 years later failed to find it. 2 competent groups, the same photographs, opposite conclusions. There are 2 more cases that circulate widely and deserve correcting rather than repeating. The first is a mass stranding of beaked whales in the Canary Islands in 2002, which is frequently attributed online to a solar storm disrupting the animal's magnetic sense. The peer-reviewed investigation found something else. The stranding coincided with naval sonar exercises, and post-mortem examinations found lesions consistent with acoustic trauma. It is a real tragedy with a well-supported cause, and the cause is not space weather. The second is a set of famous racing pigeon disasters in the late 1990s, in which the great majority of birds released in certain long-distance races simply never came home. These are routinely presented as evidence of solar interference with a magnetic sense. There is a serious competing explanation, argued in detail by a researcher who went back through the individual race records, attributing several of the specific incidents to the disruption of low-frequency sound cues, including, in at least one case, the shock wave of a supersonic aircraft passing over the route. Pigeons appear to navigate partly by infrasound, listening to something like an acoustic landscape, and the losses line up with the acoustics better than they line up with the field. Neither correction means the animals lack a magnetic sense. Pigeons almost certainly have one. What the corrections mean is that when a large number of animals do something inexplicable, magnetism is an attractive explanation precisely because it is invisible, and invisible explanations are the easiest ones to reach for and the hardest ones to check. I bring these up because they are the honest boundary of this subject. The Robin result is supported by 6 decades of behavioral work, a specific molecule, and an experimental signature that essentially nothing else could produce. The dog result is one careful study and a set of failed replications. Both are magnetoreception claims. They are not the same weight of claim, and treating them as equivalent does a disservice to the strong one. Which brings us to you. In 1992, Joseph Kirschvink and colleagues published an analysis of human brain tissue and reported finding magnetite, real, ferromagnetic, single-domain crystals, on the order of 5 million per gram of tissue and up to 100 million per gram in the membranes surrounding the brain. The crystals are there. They are biologically produced rather than contamination, judging by their uniform size and shape. What they are for, if anything, nobody knows. They may be a leftover from a distant ancestor. They may be doing nothing at all. Then, in 2019, a team including Kirschvink ran a careful experiment on people. Participants sat inside a shielded chamber, a Faraday cage with coil systems that could produce a field the same strength as Earth's, and rotate its direction with no sound, no vibration, and no mechanical cue of any kind. Their brain activity was recorded with electrodes on the scalp. In a subset of participants, something happened. The power in the alpha band, the 8 to 13 Hz rhythm that tends to be strong when the brain is idle and drops when it engages with something, fell measurably, time-locked to specific rotations of the field. The effect was strongly asymmetric. It occurred for rotations in one direction of a downward inclined field, and not for the mirror image, which is difficult to explain as an equipment artifact, because equipment does not usually care about handedness. Not one participant reported feeling anything, not a sensation, not a hunch, not a flicker of awareness. When asked afterward whether they could tell when the field had changed, they could not. I want to be honest about the status of this. One laboratory, one set of experiments, not broadly replicated, in a field with a long history of results that did not survive. It is not proof of a human magnetic sense, and nobody involved has claimed it is. But sit with the possibility for a moment, because it is a strange one. There may be something in your head that responds to the orientation of this planet's magnetic field. It may have been responding your entire life, every time you turned a corner or lay down to sleep, facing a different way. And the signal, if it exists, goes somewhere in the brain that never bothers to tell you, filed and never mentioned. A sense with no sensation attached. Which brings us all the way back to where we started tonight, because there is one more thing to say about humans and this field, and it is not about magnetite. We cannot feel it. Whatever is or is not happening in the alpha band, no human being has ever had a conscious experience of the magnetic field of the Earth. We are, sensorially, locked out of an entire layer of physical reality that a bird in a hedge apparently sees as a shape in the air. And of every species on this planet that lives inside this field, we are the only one that has mapped it. I promised you at the start of tonight that I would answer the question in the title plainly, and not soften it, and not dodge. So here is the answer. We cannot explain magnetism, because explaining something means reducing it to something more familiar, and there is nothing more familiar than the electromagnetic field. That is the whole of it. Everything else tonight has been the working. Let me unpack that sentence, because it is doing more than it looks like it is doing. When you explain anything, a disease, an engine, a weather pattern, a slip on the ice, you are translating an unfamiliar thing into a set of things the person you are talking to already accepts. The engine works because expanding gas pushes a piston. Fine, if you accept gas and pressure. The disease spreads because a virus copies itself in your cells. Fine, if you accept cells and copying. Every explanation is a translation, and every translation needs a language on the other side. Physics has spent 400 years pushing the language further and further down. Oersted merged electricity and magnetism. Maxwell turned them into a field and got light for free. Einstein showed the split between electric and magnetic is a property of the observer. Quantum mechanics gave us spin. Heisenberg showed that ferromagnetism is really electrostatics, constrained by a rule about identical particles. Quantum electrodynamics turned the field into a quantum object and predicted the magnetism of a single electron to 12 decimal places. Gauge symmetry explained why charge is conserved at all. Every one of those steps is real, and every one of them was hard-won, and every one of them made the description more accurate. And at the bottom of all of them are three statements that have nothing underneath them. Charge exists, spin exists, the electromagnetic field exists. Ask why an electron has electric charge, and physics has no answer. Ask why a point-like object, with no size and nothing rotating inside it, should have a magnetic moment, and physics has no answer. It will compute the moment for you, to a part in a trillion, but it will not tell you why there is one to compute. Ask why there are no magnetic monopoles when the mathematics has an obvious empty slot for them, and physics has no answer. Ask what a field is made of, and the honest reply is that it is not made of anything. It is one of the things the universe is made of. You can push the mystery around. You can say that electromagnetism is required by demanding a certain kind of symmetry in the equations, and that is a true and profound statement. But then ask why the universe has that symmetry, and you are standing on the same floor, in a different room. It is worth seeing exactly how that relocation works, because it is the most fundamental answer modern physics has, and it is genuinely beautiful, even though it does not finish the job. The electron is described by a quantum field, and that field has a phase, a quantity a bit like the angle of a hand on a clock, which has no directly observable value on its own. Now make a demand. Insist that you should be free to choose that phase independently, at every point in space, and at every moment in time, and that nothing physical should change when you do. That demand, by itself, does not work. The equations break. To repair them, you are forced to introduce another field that adjusts to compensate for your choices. The field you are forced to introduce is the electromagnetic field. Its ripples are photons, and the conserved quantity that comes along with the symmetry is electric charge, the same idea that turns any continuous symmetry of the laws into a conservation law. That is a real explanation, and it is the closest thing we have to an answer to why electromagnetism exists at all. It says the force is not an optional extra bolted onto the universe. It is the price of a particular kind of freedom in how the equations are written. And then you ask why the universe has that freedom, and the flaw is right there again. There is one more layer worth mentioning, because it undermines even the sense in which magnetism is fundamental. Above an energy scale of around 100 billion electron volts, electromagnetism and the weak nuclear force stop being two forces and become aspects of a single interaction. The photon we see at ordinary energies is a specific blend of two more basic fields, mixed together by the way the vacuum settled as the early universe cooled. Which means the electromagnetic field, the thing we have been calling irreducible all night, is itself a leftover of a symmetry that broke, a long time ago, for reasons that are also not fully explained. And the theory that predicts the electron's magnetism to 12 digits contains a step several of its own architects distrusted. Making the calculations finite requires a procedure called renormalization, which Feynman himself described in print as a shell game, and which Dirac never accepted for the rest of his life. The most accurate prediction in the history of science rests on a piece of mathematics that some of the people who invented it regarded as a swindle that happened to work. This is Feynman's answer, and I want to return to it now that we have earned it. When he was asked what is happening in the gap between two magnets, he did not say the question was silly. He said that a why question can only be answered by translating into things you already accept, and that with magnets, you run out of things to accept almost immediately. The chain of why questions does not end with a revelation. It ends with a shrug. And the shrug is not a failure of physics. It is the structure of explanation itself, showing through. Because it is. That sentence sounded like an evasion when I said it at the beginning of the night. I hope it sounds different now. It is not a refusal to think. It is what is left after 4 centuries of the best thinking anyone has done. After Oersted's compass, and Faraday's ring, and Maxwell's equations, and Einstein's moving conductor, and the split silver beam, and the theorem that says none of it should be possible, and a measurement accurate to 12 digits. You are entitled to say, because it is only after you have done all of that and found that the flaw is still there. I want to give you one last piece of strangeness before we finish, because it is small, and it has been sitting under this whole video. The magnetic force does no work. That is a standard result, and it follows from the shape of the force law. The magnetic force on a moving charge is always exactly perpendicular to the direction it is moving, and a force at right angles to motion can change direction but cannot add energy, which means that when a magnet lifts a paperclip off a table against the gravity of an entire planet, the magnetic part of the force is not the thing doing the lifting. Energy is definitely being transferred. The accounting has to be done through the internal structure of the material and the electric fields induced as things move. Even the very first thing you ever noticed about a magnet, that it picks things up, resists a simple statement of what pushed what. The subject is like this all the way down. So let me close where we started, at the refrigerator door. The question written on the thumbnail of this video was not a stupid question. It was mocked for years as a punchline, and it is the last question. It is the point at which a person holding an ordinary object in an ordinary kitchen walks in one sentence straight to the edge of what physics is able to say. There is no shame in arriving there. Almost nobody realizes how short the walk is. And here is the part I find genuinely moving, and it is the reason I wanted to make this video. We cannot feel it. Of all the animals living inside this planet's magnetic field, we appear to be among the ones with no access to it at all. A robin in a hedge at dusk apparently sees it as a shading across the world. A bacterium in the mud is turned by it without knowing. A turtle hatchling reads its own position on the planet from it. And a human being stands in the middle of the same field, with the same field passing through the same body, and feels nothing whatsoever. We were locked out, and instead of being locked out, we noticed a rock that pointed, and we got curious about it, and the curiosity did the work the organ would have done. That is the sequence, and I want to lay it out because it is one of the better things our species has done. A stone that pointed south became a diviner's spoon. The spoon became a floating needle. The needle went to sea. Somebody noticed the needle did not point exactly at the pole and wrote it down without being able to explain it. Somebody else cut a magnet in half and found he could not separate the poles. Somebody ground a lodestone into a ball and realized the whole planet was one. A compass twitched near a hot wire. A ring of iron kicked a needle in another circuit. 4 equations produced light at the right speed. A patent clerk removed the absolute frame. A cheap cigar developed 2 spots on a glass plate. A theorem said none of this could happen classically, and it was right, and the magnet on the door is quantum mechanics at hand height. And in the end, we built machines that generate fields 50,000 times stronger than the planets, and we point them at a living human head, and by leaning on the alignment of about 1 proton in every 200,000, we take a photograph of the inside of a brain that is still thinking. The robin has the sense, we have the question, and the question, it turns out, travels further. So the next time you take something off your refrigerator door and put it back, and you will, probably tomorrow, I would like you to notice the small click as it grabs. Underneath that click is an electrical repulsion held in check by a rule about identical particles, expressed as a relativistic residue of charges moving slower than a snail, mediated by a field nobody can say is made of anything, in a universe that permits none of it classically. Every part of that sentence is true, and it is measured, and it is one of the great achievements of human thought. And it still does not tell you why. It is the most mysterious force in physics, and after everything we have built on top of it, we still cannot explain it. I do not think that should trouble you as you fall asleep. I think it is the most interesting thing about the object on your door. Thank you for spending this time with me, and for coming all the way down through the layers of something almost everybody walks past. If this kind of slow, patient exploration is something you value, a like or a subscribe would mean a great deal. It is what lets me keep making these. And remember, the next time a magnet clicks onto a door, you are hearing the edge of physics from about a foot away. Good night, and may you never look at your refrigerator the same way again.